Hi, I'll just make a short description on how to make the solar resource calculation in the spreadsheet I've provided. Basically, most you need is these formula on the right hand side of the first sheet, where we got latitude and longitude for our site, and by setting in, for example, day of year and time of day, we get declination, meaning the angle of the Earth compared to the rotation around the Sun. Sunrise, sunset is not so important. Then we get our angle, elevation of the Sun for that given hour, and azimuth, meaning the angle compared to south. So basically it's mostly these angles that we need at first. Then we need a little extra calculations to find out what is then the solar radiation given these angles. To calculate that, you can either look at the PowerPoint, or you can look here in PV-CD-ROM in chapter 2, properties of sunlight, specifically 2.4, terrestrial solar radiation. We got the different effects on the solar radiation: declination angle, elevation angle, azimuth angle, all of these that we had already included in the spreadsheet. Sun position basically also. Solar radiation on a tilted surface, meaning a surface pointing directly towards the Sun, azimuth-wise, but in a tilt. And then in arbitrary orientation and tilt, we have a calculation where we can calculate the module radiation depending on the incident radiation, and then an angle calculation that will take into consideration both Sun elevation and azimuth, as well as the collector elevation and azimuth. So basically we need this equation also to be able to calculate module radiation. Going back to the spreadsheet, this first spreadsheet is making calculations for each day. Basically I would rather like to make calculation each hour of a day all over the year. So what I did is that I copied these equations, or these calculations, to the second spreadsheet, hour of day, over here, and then I used these formulas. I copied them over here in the spreadsheet and pointed to the right cells in the spreadsheet. And now I've got a spreadsheet consisting of all 8,760 hours of the year, 8,784 on a leap year. But You could also do the calculations per quarter of an hour to get it more accurate, but per hour is okay. So I got time and date plus 1 hour all the time, every hour of the day, and which day of year, which is the input I need for my calculations. And I've got a calculation for declination copied from the calculation over here. So I've got this equation inputting the day of year, and from that I can calculate my declination. Solar time is basically the hour of day. An hour angle is the angle linked to that solar time, going from minus 180 to 0 in the midday, and again to 180. Then elevation, I've got copied the formula for elevation over here, and of course linked to the right cells here. And also I've got azimuth calculation. Now I've basically got all of the inputs that I would need for this here calculation, where I needed both the elevation and azimuth of the sun, and then I need elevation and azimuth of the solar panels at Dronninglund. When I got these, I made a formula where I set in these parameters. Basically what I also did is that I say if the elevation is below 0, if G2 is higher than 0, then it should make this calculation, and if it's not higher than 0, then it should just mark D as a non-number, because of course there will be no solar radiation when the sun is in minus elevation. So up until the sun goes in plus in elevation, there's no incident radiation. And then when the sun goes above the horizon, we have a calculation depending on elevation and azimuth of the sun. And in Dronninglund, as far as I can see, they have an elevation of the solar collectors of 30 degrees, and they have azimuth 0 degrees. So this will then give me these numbers for solar radiation. Here I've just used 1000 watts as the incident radiation as described in the assignment. You could also go a little further if we look at the next slide here in PV-CD-ROM, calculation of solar insolation. There's in the bottom here a formula where we can calculate the direct component of sunlight depending on air mass, meaning at lower elevations there will be lower direct radiation because of a longer path through the atmosphere. So we got 1350 watts per square meters from outside the atmosphere, and then we got this small equation taking into account the air mass. So I tried to take that into account also. First calculating zenith angle, because when I need to calculate air mass, the air mass is the same as 1 divided by cosinus to the zenith angle, meaning the angle from directly up from upside. We have here our zenith angle, saying that again, if my elevation is below 0, then of course I have no zenith angle. If it goes higher than 0, then the zenith angle is the same as 90 degrees minus the elevation. So very high zenith angles here in the winter time. With zenith angle I can calculate the air mass, and from it then I can take my direct solar radiation calculated from this formula, and from that I can again calculate solar radiation, where I've got, instead of the 1000 watts per square meter, I've got this number from here times the angles. And I've got numbers for every hour through the year. 1 hour we've got a medium power in watts times 1 hour, meaning I've got a number of watt hours in the formula here. And then I can just go on and summarize how many watt hours that's produced every month through a year, and the whole year in total. Hopefully that would get you a bit further on the assignment.